Hello and welcome. Last lecture we began the theory of the integration of forms on a manifold. So we didn't quite integrate anything in the previous lecture. Instead we introduced a notion, namely that of a volume form. So volume form omega is a nowhere vanishing n form on a manifold of dimension m. So if you have an m-dimensional manifold, M, big M, so if omega is an M form, and it vanishes nowhere, then it's a volume form. So these things are rather special because they allow us to build theories of integration on manifolds, and as we'll see, we can use these objects on lower dimensional submanifolds and also develop a theory of integration over submanifolds as well. That's going to happen soon, but now we've got to go through a little bit of drudgery to build up this theory of integration before we can use it in all its glory. Before I do that, I'll just remind you that if M is orientable, that implies there exists such an omega. Now, whether or not this is the right omega, that depends on extra data. So it turns out that at this stage, we don't really have enough structure on our manifolds to select out a canonical or correct volume form. And in fact, if you want to get a canonical volume form, you need a data of at least a Riemannian metric. When you have one of those things, then you have enough extra data to say what you think the right volume is for a piece of a manifold. So this means that the theory of integration we're going to build will be a function of something that's arbitrary. Like we won't be able to select the right one. We'll just build up our theory, and whenever we have such a volume form, then we'll be able to do a theory of integration. And then to choose the right one, we'll need extra data such as Riemannian metric or, to some extent, symplectic structure. Good, that was what we did last week. And now, let's actually do some integration. So let f be some function from our little m-dimensional manifold to the real numbers, real but real valued function. They live inside calligraphic fm, these functions. And let's suppose that someone came and gave us a volume form, or that we just had a reason to prefer one particular volume form. At this stage, we have no reason to prefer one over the other. So that's fine, or sometimes we call these things volume elements as well. And then to build the first step towards our integral, defining our integral on the manifold, we're going to take, well, a coordinate neighborhood. So that's a pair of an open set U, some function phi from our little m-dimensional manifold to Rm. There's U, phi, Rm, and on this manifold we have this volume element omega, and we have some function to the real line. That's currently the data we have. And given this data, that's actually enough to build a definition of what an integral of f over the little region U looks like. What is this thing? We can give a definition for that. So the idea behind the definition we're going to supply is simply the same idea we've been applying throughout this review of differential geometry. Namely, whenever you've got something on the manifold, quickly get it onto Rm where you know what to do. Once you've got it on Rm, then you're good, right? Because there you can use multivariable calculus to do whatever you wish. So that the main difficulty is in associating to a function here, a function down here. And then once you're there, you can more or less define an integral just by analogy with the many variable calculus case. And okay, we're just going to define this thing. And then so f times omega is again an M form. Right? F's a function, so it's just a number times by an M form. So the integral of the M form f omega over U is defined to be, so this symbol here, whenever you see it, don't try and interpret the symbol. First, replace the symbol by what's on the right-hand side of the definition. So you first do an integral over a region in Rm, namely this region. And what do you integrate? Well, you want to integrate a function from Rm to R. How many functions are there from Rm to R? Well, there's one canonical one. There's one function that you would naturally write down. And that is first do phi inverse to go from Rm to the manifold, and then do f. I hope I got it the right way around this time. So f composed with phi inverse. So we need a function from Rm to R. We have a function right there, f composed with phi inverse. And we have a little bit more, actually, that we need. We need, you know, this volume form here has to play a role somehow. And it's going to play a role when we express it in terms of this coordinate basis here. So I'll add in that extra information here. So this H m. This little h comes from expressing our volume form omega in terms of the coordinate basis as dx1 through to dxm. I should put those as superscripts. And I guess for consistency, I mean, I'll put them as superscripts up here. Although that distinction is not really made in many variable calculus. So there it is. That's what you do. Whenever you see this, you immediately go to the coordinate representation for omega, take your function f. H is also a function from Rm to R. And just replace that symbol by this symbol and you're good to go, because this is something you do know how to process with many variable calculus. Now, why would you choose the definition to look just like this and not different? I mean, what's with the h, right? Maybe you could just drop the h and just, why not take it to be this? Well, it's all got to do with what happens when you go from one chart to another. You want that that things in the intersections between two charts, that these definitions match up, that they're well defined. And that's why you have to choose things this particular way, because when you change basis, remember volume forms change basis in the right way to match how the integration measure changes under a change of coordinates. So that's why it looks exactly like this. To make that notion well defined. Because it's very tempting, right? Well, it's tempting for me. I don't know for you. It's tempting just to say, well, why bother with volume forms? It looks like we have enough data here already. We have the manifold, we have u. I didn't, you could write down this as a many variable function from Rm to R. Why don't I just define the integral according to the normal integral here with just the dx1 through the dxm and forget this h nonsense? Why not? Well, if I was to then look in another patch, then there would be a problem when I compute the integral in the intersection between two charts. And the volume form is exactly the thing, exactly the extra information that tells you how to change integration measures between patches. So I hope that if you're sort of troubled by this definition, if you ponder like, why doesn't the naivest thing work, that you'll be sort of convinced after a while looking at different charts that it can't work in general. You need this extra data of a M form omega. Okay, that's great. So we can integrate over a coordinate chart. Super duper. But that's not like integrating over M, is it? So that presents further challenges. How do we integrate a function over all of M? Surely that's something that's we should be able to do. All right. You can do it, but you need extra information. So the first step is to at least cover M with a bunch of charts. If you can't cover M, then well, it's hopeless. So we want to cover it with open sets. That's actually, the word open is kind of important here. Although you'll never notice it in examples. Locally finite means that every point is in at most a finite number of these sets. And covering means what it means. That if you take the union of these UJs, you get M. So let's suppose we've covered our manifold with a bunch of open sets. Locally finite, very important. Open, also important. And the idea is simple, right? How am I going to integrate f? Well, I just integrate the function over all these charts and add it up, right? But you should see a problem here. If you do this, if you cover M with a bunch of a locally finite collection of open sets, let's see what the problem is with defining an integral over M. So here's a really good example of a manifold. It's the two-sphere. Let's cover it with open sets. You could imagine doing this, right? So we cover the sphere with little circles. Is it locally finite? Well, I mean, I can't prove it to you with this picture, but that point there is in 3 open sets and so on, right? You just look around, is every point in at most a finite number? Well, yeah, there's even just a finite number of open sets here. So it's locally finite. These are open, we don't include the boundary. And now let's imagine we have some function f to the real line. Okay, how are we going to define the integral over the manifold? It's very easy, isn't it, right? Integral of f omega is equal to question mark, exclamation mark. What's wrong with this?
We'll be covering some of the portions twice.
Exactly, we'll be overcounting some of the contributions. Oh, that's a bit of a problem, isn't it? See, if this particular point here will get counted like 3 times in this integral definition over here. So this is a bad definition. I mean, you can define it, but it's just like, it's clearly not right. So a bit frustrating. How are we going to fix this up? So the way to fix it up is you agree on a way to fix the overcounting in the intersections. So a way to fix the overcounting would be to like say, okay, I'll only take a third of the function from this. I want to do the integral over that one, a third from that one, and a third from that one. Seems simple enough, right? Should work. But now you have to be super duper careful. You have to be very careful. That is indeed the right thing to do. You agree on every point that it gets overcounted, that the overcounting is dealt with by agreeing on an amount to contribute from each of the patches that it's in. It's indeed what you do. But you have to be careful because that method of agreeing of how much of the integral from this patch here do you take, and this patch here, and this patch here, that's like some weighting of these 3 integrals there. That weighting is itself a function, and you want to make sure that that function is integrable. I mean, it's possible to use the axiom of choice to construct some extraordinarily baroquely complicated function that will, at every point, give a weighting that adds up to 1. But is that function integrable? Is that a Riemann integrable function or a Lebesgue integrable function? All we know is that smooth functions can be integrated. So the weighting, whatever we choose as our weighting functions, has to be smooth. And then it's really not clear if you can agree on a weighting which is smooth across these patches. So let's at least define the thing we're after, and then I'll say a couple of words about proving that that thing does exist, that we can indeed find a smooth family. So where was I? Up there, definition, right? So we're continuing this definition. Continued over there. So if we have a family of functions epsilon j and these epsilon j's go from uj to r, so if this family will turn out to be a weighting scheme, satisfies some conditions, then it's a good weighting scheme. So firstly, if you want to have a weighting, then it's got to be above 0, otherwise you have like, it's not really a weighting anymore, is it? So the value of our function, of each of these functions, has to lie between 0 and 1. You know, we want to weight our each of these integrals in the overcounting regions by something like a probability, right? And secondly, we want that these functions are identically 0 if, well, here I've got to put in a coordinate, if Q is not in uj. Now, that is well possible, right? And there's a further requirement. Well, is it possible? Actually, I'll say a comment about this in a minute. The function is going to be differentiable yet be exactly 0 outside of some, let's say, compact region. Is that even possible? You should worry about that. And you want that the sum of all these functions, and this is, since this is a locally finite collection of open sets, there's a finite number of these things in each of these sums. You want that that's equal to 1 for all points in the manifold. Yo, a question?
The second criteria, this isn't equivalent to the support being in U, right? Because the support is the closure of what is kind of written there.
So the question is, isn't this equivalent to the support being in the closure of U? Yes.
No, the claim is that it's not. Because the support is the closure of the set that is kind of described.
The support is the closure of the set where
the support is closed and has to lie completely within
an open set. Right, yeah, that's exactly right.
But that's not what
That's not what's written here, that's true, yeah.
Okay.
That is true. Yeah, okay, that's not very nicely formulated. So the support of epsilon j, which is closed,
Yes.
what we really want to say is that. Yeah, that's not quite correctly formulated. So if you have a bunch of differentiable functions that satisfies these criteria here, and we can give it a name. It's called a partition of unity. Such a thing if it exists. Oh, partition of unity subordinate to uj. Blech. Okay. If you could find such a thing, if such a bunch of functions really did exist, then they would be exactly the right things to put in here to find an integral over your m, because it would deal with the overcounting at every point. So we'll just assume that such a bunch of things exists.
Maybe one other question while you're
Yep.
you said we don't use like weaker than smooth functions in order for the integral to converge, I guess?
So the question is, we don't use weaker than smooth functions in order the integral converges. No, it's not convergence. It's
Or
to do
like-
with integrability at all.
Okay, integral.
Because you can construct non-integrable functions very, very easily
But-
if they're not smooth.
But continuous is like
Continuous is enough, but
sufficient.
they suppose that nowhere does it say, apart from here, that these functions have to be continuous.
But differential is stronger than
Differentiable is stronger and implies continuity, and so everything's fine. That's why that's there. So I was expressing the counterfactual point that if these functions were not even continuous, then it's not clear what to do.
Okay.
And but the not continuous weighting functions are easy to dream up. So the difficulty is in dreaming up a bunch of, or a partition of unity where these epsilons are at least continuous, or if not differentiable. Right? So that's the difficulty right there.
So is it a difference? Because I can see why we want smooth, a smooth partition of unity, but then we have kind of an agreement between like a local integral over a form,
Yes,
local integral over a form, because the form is
smooth.
spheric, yes.
It's important that the functions are smooth. Yes,
Okay.
that's I'm not making a strong point here. If the functions aren't smooth, then you're in for trouble. Maybe that's
So that then things start to not agree with what you else define.
yes, that's right. If you choose a non-continuous partition of unity,
Yeah, I wouldn't do that. Continuous.
you wouldn't do that, right? That's why at least continuous should be in the notion of partition of unity. But why not work within the category which we're working in, which is that of smooth and differentiable functions? So that's why we add differentiable there. But now I want to make the point that not continuous partitions of unity are easy to make. That's trivial. You just at every point just choose a probability distribution. But differentiable partitions of unity, do they even exist? There's a tension here between this criteria here, this adjective differentiable, a tension between that and these three criteria here. And so that challenge, that tension, we have to resolve that. And I have to at least say some words about, do these things exist? I mean, obviously they do, because I've put it in a definition, but I have to explain to you how to resolve this tension. Well, firstly, let me at least write out the integral. I mean, I hope it's kind of clear now. So property 3 implies that for all points in the manifold F, you can add in 1, right? F of q times 1 is f of q. And what does this do? Well, this defines a bunch of functions, f of j of q. So for all q in the manifold, we see that f of q is the sum of these f of j's. And these f of j's are none other than these things. These f of j's are smooth functions, so they're integrable. And hence, and also fj equals 0 outside the u of j's. And so the integral of f over m is given by just the sum of these integrals. Like that. Okay, there's a little exercise. Show that you get the same answer if you chose a different atlas. So I'll say a couple of words about these epsilons, these partitions of unity. I've erased them. We're after, there's still the epsilons up there. We're after functions that are smooth because we want to still retain or remain in the category of smooth functions as morphisms. But we also want that a function that is smooth yet vanishes outside some finite region. So if you can convince yourself that such a thing exists, then I hope that the construction of a partition of unity becomes plausible. So the main difficulty, I claim, is in finding a smooth, compactly supported function. That's the main difficulty in building one of these partitions of unity. And once you've got one, then you can use it, you can sort of stretch it and deform it, and then use it to construct these epsilon j's. So we're after a function f with a... Basically, if you can do it from R to R, then you can do it from Rn to R, and then you can do it from coordinate patches. We're after a function f that goes from R to R that is smooth, so you can differentiate it an infinite number of times, and these derivatives are continuous. And, for example, f of x is exactly 0 outside of some interval, say -1 to 1. Because once you've got one of these little beasties, then you can stretch it, deform it, multiply them, take their products to get further compactly supported smooth functions. Now, I've been sort of careful to say the word smooth and not analytic here. So it's a distressing theorem that there does not exist doesn't exist a compactly supported analytic function. It's what every physicist wants, but you don't get to have it. These functions must be non-analytic. I'll show you a couple of steps of how to construct such a thing. You might start to wonder, is it even possible at all? So you've got to have start somewhere. And so I'm going to show you a very special function that is not compactly supported, but vanishes identically in some region and not in another, and is smooth. And here's the magic function right here. It's e to the minus 1 on x for x is greater than 0, and 0 for x is less than equal to 0. This is a very magical function. So this is our sort of fundamental building block to get these things here. So start thinking about that function. So when x is really small, x is positive but really small, then you've got 1 over x in the exponent here. But that's really big. And e to the minus something big is really small. So this is obviously getting very, very close to 0 as x goes to 0 from the right. And what about when x is extremely very large? Well, when x is nearly infinite, then that's like 0, and e to the 0 is like 1. So that's a kind of interesting function. And now, all I've just argued is that this function goes to 0 near 0 and is 0 to the left. What about the derivatives? Do all the derivatives exist? Well, start differentiating it. You'll get some function times by e to the minus 1 over x. That function will be a polynomial in 1 over x. And as x goes to 0, the exponential beats it every time. So it will exist. The derivatives with respect to x exist. So it's smooth. It's not analytic, but it's smooth. So let's draw this function. What does it look like? Well, it's easy to draw, right? So it's 0 here. This is x. And over here it's 1. Asymptotically over there it's 1. So it sort of comes in. You can draw it on the computer if you want, and it sort of becomes identically 0 there. Now the trick to building something that's compactly supported, well, I've got that function, haven't I? I know how to construct this. I could use translates of this function now, couldn't I? I could translate it to the left. So you move it left by 1 unit. This is obviously this is not compactly supported, but it obviously vanishes left of minus 1. I could take a reflection of this function, that would also be one of these functions. And I could take the product. So, like this, I could multiply 2 of these guys. So this function here is, what did I call it? I didn't give it a name. Let's call it F, G, H, E, D, C, C. So that function there is c of x plus 1. Right, when x is minus 1, then the argument's 0, so that's this one there. And this dotted function here is c of reflection minus x minus 1. And if you take the product, you could define a function b of x to be c of minus x minus 1 times by c of x plus 1. Boom. That is a function definitely is 0 outside of minus 1 and definitely 0 past 1. and is smooth, right? It's a product. Looks exactly like this if you plot it. It doesn't quite go up to 1. You just rescale it a bit. And then you're done. You've found yourself a nice function that's compactly supported. It's identically equal to 1, say here. Now that's not quite the construction. We actually want a function that's identically 1 on some region, identically 0 on another region, and smooth in between. I'm not going to show how to construct that, but you can see by doing a transformation which scales infinity down to 1 that we can get such a function. So I haven't given anything resembling a proof that smooth partitions of unity exist. What I've shown you is how to construct a smooth function. I've argued how to construct a smooth function that's identically 0 outside of some interval. To get a partition of unity, you want to build functions that are identically 0 outside of arbitrary compact sets and are inside an arbitrary compact set. And to do that, you use some combination of these functions and scalings and mappings thereof. And then you've got to argue that that you can extend one of these compactly supported smooth functions to a collection of them that add up to 1 everywhere. It actually turns out to be not so difficult to carry out that proof. You just have to be a little bit careful. Then that shows you the existence of such a thing, and then you can at least write down an integral, and then this exercise shows that that integral is independent of the partition of unity and of the charts you choose. So if you go look up the proof now, I think, at least I think it's in the book of Warner on differential manifolds. They go through the gory details of constructing this partition of unity. You'll see that the ideas are there, already captured by this argument that I've given. So it's obviously a pretty good idea to do integrals of functions on manifolds. This is something you might want to do. It's a good thing, right? And what we want to do is extend this notion of integration down to submanifolds. But before we do that, let's do an example. So you can see how this works in action. Let's take our favorite manifold, S1, the circle. Here I've drawn it embedded in R2. And we're going to have 2 charts on our circle. We can't have one chart. There's no way to continuously map a circle to the real line. And so we're going to take 2 charts. We're going to take a chart that goes around this part of the circle there, but does not include this point here. So this point is excluded in chart number 1. And we'll take another chart which goes around here, but doesn't include that point. So those are our 2 charts of the circle. They're all meant to be on the circle. It's all meant to be on this one there. So let's just define some charts right here. Some coordinate functions, phi. So phi 1 inverse, I'm going to define it by the inverse, maps from the interval 0 to 2 pi to the circle by the following function. Give it theta, and it will hand you cos theta, sine theta. So when theta is 0, this is 1 comma 0, it's this point there. When theta is 2 pi, just rolls around. Oh wait, yeah, it's this. We don't have 0 in the interval. So when theta is 0, it is that point there, but that point's not included. So this is actually chart U1 here, and that's chart U2. So as theta rolls around the interval 0 to 2 pi, phi rolls around that chart U1. And we've also got phi 2. Phi 2 is exactly the same, but it goes from minus pi to pi. Exactly the same functions, in fact. Okay, we've got ourselves a nice atlas of the circle S1. It's covered by 2 charts, and we have the coordinate functions right there. You should go ahead and work out the transition functions as an exercise. All right, let's do an integral. Let's integrate cos squared theta on S1. Well, we know the answer, right? It's an embedded manifold. We can go ahead and work out the answer the old-fashioned way. But let's tie our hands behind our back and do it as using our definition of integrals. And so for that, we need some partitions of unity. And we have one by choosing epsilon 1 is sine squared theta over 2, and epsilon 2 is cos squared theta on 2. Let's check, is this a partition of unity? Does it vanish outside of U1? So epsilon 1 has to be compactly supported. Well, it is. It has to vanish outside of U1. And it does, right? It's only one point that you have to worry about. Namely, theta is 0, and there it's exactly 0. And epsilon 2 has exactly the same property, but for U2. And then we choose as our integral, as our volume form, just d theta in the coordinate chart. And then let's do our integral. So integral over S1 of the function cos squared theta d theta is the sum u1 goes to 0, 2 pi. I skipped a step. No, I didn't skip a step. And it's a fun little exercise to show that that's a half pi plus a half pi. In fact, that's just pi. Tests your antiderivative skills.
Another question.
Yep.
Just thought of it. We defined like here it is perfectly clear. That's the sum over all the neighborhoods.
Yes.
Or like the sum of the covering. But we didn't say a thing that it has to be countable.
It's locally finite, so
It's locally finite, but then we add up all the.
you add them all up, but only a finite number will ever be non-zero at any point. So the
Oh, I see.
Yeah.
I think, yes. Okay.
so you can do sums of uncountable sets as long as
Yes.
only a finite number of terms is non-zero.
And to the other thing, this is exactly an example of.
It's exact example of a compactly supported analytic function, isn't it?
Yeah, no, not really. Yeah, okay, but what I mean is this is an example of where this condition 2 is like where it's a difference because the support doesn't lie in U1 or U2.
The support does not indeed lie in U1 or U2, yeah.
Yeah.
But you can define the integral here with limits, so it works out fine in this particularly. It's a particularly degenerate example because the coverings, the charts are open sets which exclude one single point. So everything has to be smooth so that you can extend the limits of these integration to the full compact region. It is all right, we've got a workable notion of integration on a manifold. We can take a function on a manifold, integrate it, get a number. As long as we have this data of a volume form and a partition of unity, but that partition of unity is guaranteed by locally finiteness and the other axioms of a manifold as a locally Euclidean space. But what about integrating over submanifolds? How are we going to build up such a theory? And one way to build up, well, it's not obvious. It's certainly not obvious. If you have some manifold M, and then you have some submanifold M, n of M, in this case a line, how do you build a theory of integration using what we have there? It's not completely obvious what to do. One way, and this is the way we will adopt in this course, is to break your submanifold up into little pieces, approximate them with like straight line segments or little triangles or something like that, and then pull everything back to a low-dimensional subspace of Rn, and then just use this theory of integration there. So that's very, 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 very roughly the way of building an integration over submanifolds. That's what we're going to do now. And to get started on that, we're going to talk about integration over simplices. We're going to talk about how to break up a manifold into chunks and then do an integral over that chunk. And this is different from the coordinate charts. These are really special subsets of M. So we're going to start in Rm, where Rn in this case, where we understand things very well. I'm going to introduce to you very special sets, subsets of Rn. We have a notation for this thing, the standard n simplex in Rm, Rn denoted sigma bar n, also denoted with angle brackets p0 through to pn. Is the convex hull of the points p0 through to pn, where, I got to tell you what these p0s through the pn's are. Unoriented standard simplex. So these P0, what is P0? Well, it's the origin. P1 is the unit vector along the x-axis. And Pn is the unit vector along the n-axis. And this convex hull means all the points in any convex combination. It's a set of points x such that x is the sum of pj. It's really a shame that I use p. Pj times by sj. xj, all right. Where the sum of these xj's is 1, and the xj's are greater than 0. So that's what convex hull means. Take all convex combinations of these basis points, pj.
Why the p0? 0, 0, 0.
Why do we have p0? It's just the definition of the standard simplex. There's more than one definition out there, I agree, but this is the standard simplex in R2. So it's the convex hull of these 3 points here. Sorry. That. Now, it's possible to define the standard simplex by not including P0, and then you have this one-dimensional guy, and then in 3 dimensions you would have a triangle and so on. But then the dimension of this object is 1 lower than the ambient dimension, so it's, you know, we do it this way. Now this is the unoriented standard simplex, and I've denoted it with angle brackets here. You can see that this definition, P0 through to Pn, could be just arbitrary linearly independent points in Rn. And that definition here makes complete sense, right? It's just the convex hull of these points. Whenever I write angle brackets P naught through to Pn, I mean the convex hull of those points. Now that simplex is not oriented. There's no sense in which it has a handedness to it. There's no inside and outside. Well, let me put it this way. There's no chirality or handedness to the object. You can't say it's left-handed or right-handed. You can't say you go along the simplex in one direction and there's another direction you could go along it. So I'll give those words more precise meaning in a second. So we want to give this thing an orientation. So if I drew arrows on it, like that, then that's kind of somehow an orientation of this simplex. And we want this notion of orientation because we want to talk about integrating along a path and along a surface. And for that we need to talk about what does the word along even mean. So for that we're going to need the word orientation to be defined. The best example is the one simplex. That's a little line segment. And you can talk about integrating along a line, right? But you can also talk about reversing the limits of the integral and going backwards. You pick up a minus sign, right? And so we're going to extend that notion through to all the n simplices. Here it is. Here's our first, we're going to build it up kind of inductively, this notion of orientation. So sigma 1 with round brackets, notice the difference here, there was angle brackets before, now there's round brackets. So we can depict that, we can draw. It's perfectly clear what the word orientation means in one dimension. It means you decorate the interval with an arrow, and the arrow tells you that it's oriented from P0 to P1. So you can talk about the other orientations. Two orientations possible of a line segment. You can point it that way, you can point it that way. So if you point it that way, that's obviously the same as just having P1 at the beginning and P0 at the end. But we're going to use the notation very suggestively that we're going to define this symbol here to be that. Why are we going to do that? Well, later on, we're going to add and subtract simplices. We're going to turn them into a free abelian group. We're going to allow ourselves to take two simplices and add them. We're going to add them by putting coefficients in front of them and then having formal finite sums of these things. So that, but at the moment, we haven't done that, right? I've just said that's the notation for that. Later on, we'll actually interpret that as a minus sign in some abelian group. So an orientation in higher dimensions is just a decoration of the faces with arrows. Let's go to two simplices. So we've managed to deal with orientation of one simplices. Cool. All right, we're done. So what does P0, P1, P2 mean? In that order, it means that you put arrows on these edges. Like so. It just tells you the order in which you traverse the edges of the simplex, and you stick arrows on them. And this has an orientation, right? There's now a notion of an outer surface and an inner surface, or if you like, an outwardly facing normal and an inwardly facing normal. So if you just apply the right-hand rule, then you can see the normal of this little surface piece points out of the board. So these arrows define a notion of a normal, of inward and outward facing normal. So the inward is there, that's the reverse orientation. And this notation is clearly redundant. So the orientation handed to us by that particular order is exactly the same as the orientation handed to us by writing the simplex like that. And so on. Now we can reverse the orientation by flipping an arrow. Sorry, flipping two arrows, right? No, flipping an arrow. So that's the orientation that way, but we could also have had the orientation the other way. Then the normal vector points now this way. And that's equivalent to going, let me see, I've got P0 at the top, P1 there, and P2 here. So the orientation of P2, P0, P1, sorry, P2, P1, P0 is obviously equaling to P1, P0, P2, which is obviously equal to P2, P1, P0. And again, we employ the highly suggestive notation that that's equal to minus the orientation of the original simplex here. So this is, again, just notational definition, the minus sign so far. It's not a minus sign. We can't add and subtract these things yet. We haven't given them a space to be added and subtracted in. So in general, we're going to define this notation for all possible permutations of these points. So we're going to allow ourselves to flip the arrows on any edge. We have this arbitrary notation here where pi is the permutation that brings 0, 1, 2 to j, k, l. So this is a definition of notation, and you can see that this definition of the notation is coherent. So if you choose different orientations, then the minus sign that you put in front here will be well defined. And now you see that's how we're defining orientation in 2 dimensions. What about n dimensions? Well, I wrote this up very suggestively. Because each of the things here can be extended to n dimensions. k plus 1. So this notation tells us when two simplices have the same orientation or opposite orientations. So this simplex here, this convex hull of these k plus 1 points, has the opposite orientation, there's a minus sign here, to the basic simplex when the sign of the permutation that maps these points to these points is minus 1. And it has the same orientation when they're the same. All right, I think we have time for boundaries. So for a zero simplex, otherwise known as a point, we define the notation to mean take boundary of So for an oriented one simplex, we're going to define the following notation. So still at the level of defining notation, we're not yet interpreting this as minus in an abelian group. It's just notation at this point. And then in general, we define the boundary for a k-dimensional oriented k-simplex. It's a linear combination in quote marks because we still haven't given these things a space to live in. So it's still notation. And we're going to check later that this notation is coherent with is well defined with respect to an abelian group. Defined by, so you take the boundary of sigma k, and what you do is you subtract out 1 point from the k plus 1 places where it could be, and then you put in a minus sign. So that's how we're defining this thing called take boundary of. It's this formal linear combination, because at the moment it's all formal, of k minus 1 simplices according to this notation here. You can see that that notation matches, at least in the special case k equals 1, this notation here. We'll do an example to end the lecture today, and then in the next lecture we'll show that this gives a nice map between abelian groups. I guess the word show is maybe a bit strong. I'll argue. Do an example. Let's take the boundary of the standard oriented 2 simplex. So let's follow this formula. You delete point 0, so that should be your P1, P2, and then you put a minus sign in front of the case where you've deleted point 1, and then you put a plus sign for point 2 being deleted. So that's the notation there. And then D3, so P1, P2, P3 minus P0, P2, P3 plus P0, P1, P3 minus P0, P1, P2. Yeah?
Maybe I'm wrong, but when we defined D1 of P0, P1,
Yes?
we had P0 minus P1.
Is that not matching this?
Like if we remove
Point P0.
then we have.
Oh, goodness me. There's an overall minus sign, isn't there?
So maybe it's J plus 1 today. Because then.
Wait on, what did I write?
Because there it's like this.
Sorry, I got carried away. Is this? Thanks. now it works, right?
Yeah, I think there it matches this.
Yeah, yeah. This I just calculated from this. So this is the correct thing. Right? This is good. This was not good. All right, I think we'll stop there for today. And then in the next lecture, I'm going to show you how to do integration over simplices in a manifold, singular simplices. And then I hope we'll get to something called Stokes' theorem, which will relate integrals over volumes with integrals over boundaries. And then we'll be basically done with our differential geometry, and we'll head straight on into symplectic geometry after that. Okay, that's it. Thank you very much.